Okay, so here we are. Welcome. Hello again. Have another problem to take a look at here, and this time I don't know the solution to this problem. I mean, I guess the IP address question I did know the solution, and then the one before that I thought about it beforehand and I came up with a solution, but this one is going to be a little bit more interesting, I guess, I suppose. Yeah, alright. I've actually thought about this problem before in the past, and this is a challenging question. I've thought about this problem in the past. It's a challenging question. I do not have the solution. Do not know the solution. So, here we go. Implement Rand10 using Rand7. Given the API Rand7 that generates a uniform random integer in the range 11 to 7, write a function Rand10 that generates a uniform random integer in the range 1 through 10. You can only call the API Rand7, and you shouldn't call any other API. Please do not use the language's built-in random API. Each test case will have one internal argument n, the number of times that your implemented function will be called while testing. Note that this is not an argument passed to Rand10. What is the expected value for the number of calls to Rand7 function? Could you minimize the number of calls to Rand7? N equals 1, 2 equals 2, 2, 8 equals 3, 3, 8, 10. So the challenge here, I don't call it 100,000 times, okay. The challenge here is that we need to get a number from 1 through 10 using a function with a window of 1 to 7, and we need when every number that we can get has to have the same probability. So every number 1 through 10 has the same probability. So if you call Rand7 once and just return that, obviously you're not going to get 8. You're going to have probability 0 for 8, 9, and 10, and then 1/7 probability for 1 through 7. So you got to shift some of that probability over to 8, 9, and 10. There is an approach to this problem I've seen in the past that's kind of interesting. It's a it's kind of a randomized. Basically, you keep calling the function until you get those other three, one of those other three numbers. How do you do that though? But I forget exactly how it works. But basically the idea is that like you can how does it work? The idea is that you could stretch the range. So if you did it the other way around, you had Rand10 and you wanted to make Rand7, you would keep rolling until you get a number in the range 1 to 7. All of them have the same probability of being rolled, so, and basically it won't run infinitely. It won't even run that long until you get the number you're looking for. You can prove that basically the probability approaches 1 that you'll get one of these numbers. So what you would do then, I guess you would increase the range from 1 to 7 to like 1 to 14, but I'm not entirely sure how you would do that. You multiply by 2, you would get 2 to 14, but you'd be missing the odd numbers. And then if you multiply by 2 and subtract 1, you'd be getting an even number. Well, you could do maybe, oh, you can't do that either, can you? 1 through 7, 1, 2, 3, 4, 5, 6, 7. I was going to say you could do 1 through 14, then take a coin flip, and that would give you 1 through 14, and then you can run that routine in a loop to get 1 through 10. But you can't do a coin flip either with Rand7. This is kind of a classic question too. This is like I've seen this question a few times. There's some variations of it, similar questions, and every time I struggle. Every time I struggle. Every time I struggle. How do we do this? You can't roll 1 through 7 twice. One of them even, one of them odd. Take the average of the two. No. What if you do that? What if you do two different numbers and take the average? Right? That'll give you no. Yeah, two different even numbers multiplied by two different numbers, two different rolls, divided by 2, and that gives you a number in the range 1 to 14. No, it doesn't. No, it doesn't give you the range 1 to 14. It gives you the range 2 to 14. Maybe subtract 1, give you the range 1 to 13. But the probability of each number is what? That's not equal. That's not a uniform distribution either, because there are a bunch of different ways. For instance, to get, if you did like the average to get to 7, there are way more ways to get to 7. Excuse me, than there is to get to 1. So that doesn't help you very much either. I want to be able to roll a number with equal probability in a range that's larger than 1 through 10, that subsumes 1 through 10, that includes 1 through 10. That's what I'm thinking. Let me lay down. Let me think. Just lay down and think. How do we? Yeah, man, I struggled with this question way back when. No, I not even way back when, but just I remember looking at this question a while ago, and I was like, one of these days I'll solve this one, but I don't remember. I don't remember the solution. It's how can we go? Excuse me. How can we go more than, let's see, like just 8? I mean, I know we can shift and we'll get the same probability, right? Just by adding, we'll go to, 2 to 8 or what have you. Could roll twice, maybe. We could roll more than once. Now that wouldn't work, because if you roll more than once, how those probabilities interact with each other is significant. Rolling 1 through 7, you're always going to get something 1 through 7, and rolling 8 through 14. Excuse me. You're always going to get something. Oh, I know what to do. Ah, I got it. Oh no, never mind. No, I don't know how to increase the size of the range. I know how to. Okay, I think I got it. All right, here we go. Okay. So you're going to roll. Oh man, this is complicated. All right, this is funny. Not funny, but this is complicated. All right. This is what we're going to do. We are going to roll until we get a 1 or a 2, and we're going to use that as a coin flip. Then what we're going to do is, depending on that coin flip, if it's a 1, then we're going to try to get something in the range of 1 through 5. If it's 2, then we're going to try to get something in the range of 6 through 10, inclusive. So 50-50 coin flip of which part of the range we want to get. And 1 through 5, so we roll, so we keep rolling until we get through something 1 or 2, and then pick something from 1 through 5. We keep rolling until we get 1 through 5 on 7. And then if we got 2, that's gonna be a multiplier, right? So then it would actually end up, not a multiplier. It would be you'd add 5. So it'd actually be a roll from 6 through 10. Yeah, there we go. Got it. We're gonna do implement Rand2 and Rand5, and that's how we're gonna do this. Here we go. I got it. How much time did that take? 12 minutes? Okay. All right. This is gonna be interesting. This is certainly going to be interesting. Okay. While loops. Yeah. So it's just a Rand2. So we're going to say while. So we're going to say int x equals Rand7. Right. So while x is while it's not in this range, while 1 is less than or equal to x, x is greater or equal to 2, right? Well, it's not. That's not the case. Set x equal to Rand7, right? And then return x. So we have Rand2 and using Rand7, and now we've got Rand5. It's going to be a similar thing. Int x. Now we're going to use this too, so that way we have this Rand7 is accessible to us. X is Rand7, while not 1 less than or equal to x, and x less than or equal to 5. Well, that is not the case. Set that to Rand7. And now what we're going to say is, we're going to say int coin flip equals Rand2, and if coin flip equals 1, then we're going to return Rand5, else return Rand5 plus 5. Alrighty, that's our function. That's our function. A bit complicated, but we can also actually do Rand4 instead of Rand7. Yeah, let's do it that way. That's better. And we're going to say x, we're going to say x divided by 2. Or x divided by 2. So if x is 1 or 2, it's going to be, actually we'll do it this way. We'll do a Boolean, and it's not Rand4, we're going to say coin flip really, so it's going to be coin flip. And it's going to be return the x less than 2. So that'll be, or x is greater than equal to 2, greater than 2. So 3 or 4. So we'll say if coin flip, if the coin flip is true, yeah, so it doesn't matter, one or the other. And we'll do return Rand5, or we're going to return Rand5 plus 5. It's going to be call the coin flip. And then we're going to say int, call that x, Rand5, return x, or return x plus 5. There we go. Something like this. Something like this. Alright. Let's try a whole bunch of these functions. 2, 3, 1,000, 10,000, 100,000. Let's give that a shot. See how we do. See how we do here. See how we do here. Alright. Looks good. Let's go for it. Hey! Hey! Ho! Apparently there is a way for them to check the distribution, by the way. I think they probably use like Monty Python. Or not, oh man, Monty Python. Monte Carlo. Combining these things. I like the Python programming language, and I also like Monty Python's Holy Grail. And it's Monte Carlo, so Monty Python is what it's the Monty Python method. Perfect. Sweet. Yeah. Alright, there we go. Nice. It's one way to do it. It's one way to do it. It's efficient enough. It's not particularly efficient, but good enough. You know, good enough. It's probably a way to do it that's better. Probably should check the discussion, see what it says. Yeah, let's do that. Let's check the discussion. Let's do that. Let's do that. I'm not super confident in this. This is like kind of a hacked approach, it feels like. Rejection sampling, rejection sampling. You want to go most votes. 3 lines. Really? Really? Whoa, 1.8. Oh, I didn't read the, oops, discussion. Excuse me, I made a mistake. Expected value for the number of calls to Rand. Oops. Could you minimize? I don't know how to minimize this. I don't know how to do this better. But I'll say the expected value is probably how many calls do you need to get something 1 through 4? From 1 to 7. Oh, we can do 1 to 6. Actually, that's better. Let's do it that way. I'm sorry. Did this wrong. That's actually an improvement. 1, 2, yeah, 1, 2, 3, 4, 5, 6. Right. We can actually try that. That's a lot better. Or okay, not much better. How many calls? You'd have roughly one call would give you the likelihood. So the likelihood of failure is 1 over 7. So you have a 6 out of 7 likelihood of success on the coin flip. So 6 out of 7 success means how many calls would you need on average? Well, if you fail, right? That's a 1/7 chance of failure. And then it's a 6 out of 7 chance to succeed again. So it's 6 out of 7 plus, so you get, okay, so it looks like this. You have 6 out of 7 success here, plus failure times 6 out of 7, plus another failure times 6 out of 7, infinitely, which gives you 6 out of 7 times 1 plus a 7th plus a 7th squared, so on, which this is a infinite geometric series, which this is 1 over 1 minus 1 over 7, which is 6/7 times 7 over 7 times 7 over 7 minus 1, 6 over 7, 7 over, oh, which is 1, right? The probability of success is 1, right? So this is also true for Rand5, which is just 5/7 instead of 6/7. But that's not what we're looking for. We're looking for, that's the probability of success, but the probability that you succeed on the first try is 6 over 7. The second try is 1 over 7 times 6 over 7. Third try is 1 over 7 squared 6 over 7. So the probability of succeeding at each point is so probability to n equals k. That's going to be when k is 1, this 1/7 term disappears. So it's 1 over 7 k minus 1 times 6 over 7. Right? For any particular k. So if k is 0, if k is 1 rather, first try, then this is 0, right? So now the expected value is going to be the sort of like the average. It's going to be the sum. Oops. It's really an infinite sum. I equals 1 to, we'll say, k or x. Take this limit as x approaches infinity because x is basically infinite. It's all the natural numbers that we're dealing with. And it's going to be the probability times x, times I rather. I times the probability that n equals I. This is how you can compute the expected value. I believe. Something like this. Yes? And then you have to divide this by the whole thing, x. Something like that. Is that how that works? Is that how that works? Yeah, I think so. How would you do that? I do want to see expected value. How do we have to quick review? Quick review. Kind of guessing here, but I don't think what I guessed seems correct. It doesn't seem correct. It's probability weighted average. X sub I times P of I, X sub 1 times P sub 1, X sub 2 times P sub 2. Oh yeah, okay. That is. Expectation of X is defined as, yeah, that's it. It's definition. It's not divided though. I'm wrong about that. Actually, it's not that division is incorrect. Actually, I threw that in there. I don't know why I did that. Actually, I do know why I did that. It's been a while. It's been a while. So they call this rejection sampling. Okay, no, it's because the probability itself already has, it already has this sort of quote unquote division. When you to find probabilities, you have like the number of, it's sort of like the number of things in a set of larger set of things. So there's sort of like A divided by B, where B is larger than A. That's kind of what I was thinking, why we divide by all of it. But no, this is just the weighted, this is the expectation. So expectation of I guess k. I don't know. What do we want to use? The expectation of x. Well, we called this k here, but we could make this I guess. Or even, I want to say x. I don't know what this is supposed to be, actually, this part, but this is the expectation of something. This is the expectation of this random variable, we'll call it x. Random variable x equals some value, little x, I don't know. Expectation of x, let's just do it that way. I think that's reasonable. So, okay. This p of I, so this summation I equals 1 of I times p of, this is 1 over 7, I minus 1 times 6/7. Limit as x approaches infinity. Take 6/7 here, and we're back here with, just going to write the limit. Times I. Now, what's interesting about this is if you look at a geometric sequence, so 1 plus x squared plus dot dot dot, and you say that that's 1 minus x, so that's 1 minus x to the negative first. You take the derivative, take d dx of these things, what you get is super interesting. You get, so, what you get is super interesting. You get 0 plus 1 plus 2x plus 3x squared dot dot dot, which is very similar to this structure here, right? The relationship between these values. And so when I is 1, this is 1. When I is 2, this is 2 times 1 over 7, right? So this actually matches, this sequence actually matches this one, where x is a seventh, it's 1/7. And then you can say d dx, this is negative 1 over 1 minus squared times negative 1, which is plus 1. And where that comes from is, yeah, this negative 1 comes down, becomes a negative 2, and then you multiply by the derivative of what's inside here by the chain rule, so you get 1 over 1 minus x squared, quantity squared, which is exactly, so that's 6/7 times, excuse me, 1 over 1 minus x is 6/7, this whole thing squared, which then gives you 6/7 times, this is 1/7 squared. 1/7 squared is 1 over 7. No, I'm sorry, this is 1 minus 1/7, so I did that wrong. That's just 6/7, this is 1/7. Yeah, 6/7 squared inverted, so that's 7 squared over 6 squared, which gives you, cancel this 6, cancel this 7, 7/6, which is super interesting because basically this ends up just being this thing inverted, which is really weird. You wouldn't expect that, right? It would be 7/6 expected number of calls on average for the coin flip. And then same thing, 5/7, right, is the other side of this. Basically the same formula with 5/7 of 5/7, oops, 5/7 times, and you have to add these two. 6/7 and 5/7 plus, what do we say? It's the inverted 1 minus 2/7, which is 5/7, 7 squared, 5, so it's, yeah, it's plus 7 over 5, which gives us 30, right? So this is 7 times 5 plus 42 over 35 over 30. 6 times 7, 5 times 7, 35 plus 42. Yeah. Should be more than, yeah, it should be more than 2. 77 over 30, which gives us 2.2 and how many halves? 2 and 17/30. Not optimal. So we use two calls, little over 2.5 calls, right? In our setup here. I want to minimize this somehow. Well, certainly this coin flip, see, I don't know, how do you not use more than 2? How do you not use more than, I mean, certainly use more than 1 call, but how do you not use 2 calls? You have to use at least 2 calls, right? I mean, it's got to be at least 2. How do you do this without using 2? That's a good question. That's a question I'm stuck on. How do you minimize? Yeah, how do you use less than 2? Easy solution with random 49. Random 1 through 7. Times 7 plus minus 1. We get random 0 through 48. Discard 40 to 48. Now we have rand 40 equals random 0 to 39. Modulo 10 plus 1, we get 1 through 10. But this is 2 calls. 9 out of 49 cases, we need to start over again. 40 out of 49 cases, we call Rand7 2 times. Overall, we need 2.45 calls. Okay, it's not as good as mine. That's not as good as mine. Mine's better. Mine is better. Also, I mean, I could crunch mine down into. Wait, what? Oh, solution 0. Oh, I was gonna say, okay, that's the easy solution. All right, never mind. Excuse me. Yeah. I was like, wait, wasn't this? Okay. Yeah. All right. Fair enough. Okay, I think I get it. Yeah, I get it. That's fine. So you could ditch. You could drop 40 through 48. So we reject that sample, and then we want mod 10 plus 1. Okay. Because it's 0 through 40, right? So the probability that we would get, so anything from 40 to 48 we drop. So we have 0 shows up 4 times. 1 shows up 4 times. Right. Okay, that makes sense. Yeah. So you have the second digit showing up, each one showing up 4 times. So you can just take modulo 10 and then add 1 to get 1 through 10. Okay, that's pretty interesting. I like that. 2.5, almost 2.5 calls. Okay, sweet. Intuition of improvement. It's a good answer, and you may pass an interview with the solution. Average caller is 2.45. How come it's 2.45? Did he do the? How did he do the? 49 out of 40 twice. Oh yeah. Well. Yeah, I think that's because of actually the math that I just did. Rejection sampling is just inverted. And obviously there's 2 calls to it. So function call is required to get this, to get the right sample. Right, I think that makes sense. Yeah, it's 2.45. Okay, got it. Sweet, sweet. Makes sense. Makes sense. All right. What is the limit? May seem possible. Unfortunately, even average 2 is still far from the best answer. The problem is that you generate 49 random states, waste 9 of them, and we rearrange the rest 40 states into 2 10 states. You can see that in that solution, 80% of random states waste, and we satisfy with only 20% efficiency. Did a quick math for the limit. Log 10 over log 7 is 1.1833. So let me define the following solution. Okay, how did he do this? He said 40 into 10, 80% of the random states are wasted, only 20% efficiency, log 10 over log 7. Why would you do log 10 over log 7? I don't get it. I don't get it. I guess if you do maximum efficiency, 1.1833. Is that what he's saying? Instead of 49, we use a bigger power of 7. Rand10 will consume the generated integer from stack cache. If cache is empty, we'll call it function generate. It will generate integer in the range 0, 7 to the 19th. Whoa. Excuse me. 7 to the 19th and close to a power of 10. So in this very large number, over this large number, 99.9997% of the cases it will generate at least 1 integer. And in these cases, generate 16 integers. N equals 19 is the best we can choose in the long integer range. N equals 7 is another good choice for 32 bits integer range. Solution, I got an average of 1.199 calls. Really close to the theoretical limit. What did he do? Excuse me? Okay. If cache is 0, generate. Result, cache dot top, cache pop, return result. I'm so confused. Generate. Current equals 0, range is long. Okay. For each I, current long, not sure what this means. Current less than range. Push. Okay. Okay, I think I understand. So basically you're going to generate like a whole bunch of these, a whole boatload of these numbers in like a batch. So you're not going to generate one at a time. You're going to generate a whole bunch of these, right? Because I guess that makes sense because we're calling this 100,000 times, right? So I guess you create a whole batch first. Okay. All right. So, I mean, that's one way of doing this. That's not really, I don't want to say it's not the right answer, but that's more of like it's kind of hacked, right? Because it's not, that doesn't really, I don't want to say it's hacked, but it's, I don't know, it's a pretty counterintuitive way of doing it. Let's just say that. It's not wrong. It's technically better. It's technically, probably optimal, probably better. But I guess what I'm trying to say is that it's extremely counterintuitive, but it doesn't fit the typical mold of like just calling the function one time, right? Optimal for just one call. It doesn't. You actually can no longer call this just once, and it's even more confusing because the test cases themselves call the function many times anyway. So this kind of batch approach actually is appropriate given the test cases, but it's like very unusual, I guess. But okay, interesting. Fair enough. Fair enough. So we expect that we'll call this function a lot. If we assume we're going to call this function a lot, which is true in this case, then it kind of opens up the box to a lot of different solutions that are basically you're carrying over efficiency between function calls to the same function, which is extremely unusual, right? Like it's almost never, at least with interview questions, it's almost never. I mean, that's sort of like the similar thing as like when you have the dynamic programming questions and you take the solutions you've already computed and you make it static, that memoized portion. So then now it's you carry over all the solutions you've already computed. Which, by the way, there was a function that I wrote the other day where I was like, oh, I can make the integer smaller, and I actually forgot there was another two optimizations I not I missed, but I skipped, deliberately skipped. One of them was to make my memoization portion static, so that way between test cases, there's sort of a between function calls, there's some carryover and efficiency there, and then the other one was to minimize like how much data is actually being used to capture the state, or how much right, exactly, how much memory is actually being used to capture the state, which could have been minimized quite a bit. So both of those optimizations would have carried quite a bit more of efficiency, and I probably would have gotten 100% on that. But this is super interesting. Okay, so he's doing something kind of pretty out of the box, pretty outside the box kind of a thing here. But okay, so he's going to take something from so 49 states, right? So generate way more. 7 to the 19th they went with. Okay, generate an integer in the range 7 to the raised to the 19th, and it's close to a power of 10. So in most of these cases, we'll get at least one integer. I'm not sure what that means. In all of these cases, you'll get 16 integers. Okay, I don't really think I fully understand. N equals 19 is the best we can choose in this long integer range. N equals 7 is another good choice for 32 bits integer range. Okay. Solution got average 1.99 calls. It's really close to the theoretical limit. Okay. So we create this cache. Result top pop. And okay, that's fine. So there's a cache. So when you generate N equals 19, current 0, range is between power of 7 and 19th. I equals 0, I is less than n, I plus plus. Current plus equals this long of 7 raised to the I times this random function. Okay, so I is between 1 and n, which is 19. Okay, so I think I'm trying to understand. I'm trying to follow here. It's like you are adding powers of 7. Yeah, so this is a power of 7 raised to 0, and this is power of 7 raised to the first power. Okay, and so now you're adding. So it's kind of like a what do you call that? It's kind of like a if you can imagine like an alphabet with 7 numbers, and you're randomly selecting one of those 7 numbers, each character, right? And you're adding all that together. Okay, that's fine. So you kind of generate a number this way. Okay, fair enough. So it's going to be you're going to get a number between 1 and 7 to the 19th, right? Not including 7 to the 19th. 7 to the 19th minus 1, I believe, right? Yeah, basically, if all these numbers are 6s, you would have 6 times the geometric sum of 1 plus 7 squared all the way to 7 to the 19th, and that's going to be equal to 7 to the 20th less than n. So 7 to the 18th rather. 7 to the 18th plus 1 gives you 7 to the 19th. 7 to the 19th minus 1 over 7 minus 1, but you're multiplying by 6. So yeah, you get 7 to the 19th minus 1. Okay, interesting. Okay, fine. So you get 7 to the 19th minus 1, some number in that range, and you call 19 random. You can call Rand7 19 times. Alrighty. Fair enough. Yeah, 19 times, so 19 function calls. while current is less than range over 10 times 10. So this is an interesting question also. So you get some number. Range is that huge thing. Range divided by 10 times 10. We modify the range too. So this range divided by 10 times 10. Basically, the reason why you do this is that you make the last digit a 0, right? The least significant digit, you make it a 0. You say, okay, if we're still smaller than that, if we're larger, we don't do anything. Which is very unlikely, right? That's what they're saying here. So almost every case, yeah, I mean, so divide by 10 times 10 is this guy, becomes this, and so there's one case, there are 3 cases really, where you don't generate any integers. That's kind of what they're saying is at least one, most of the time you get at least one integer after making 19 calls. After making 19 calls, you get one integer. Only 3 times, there's only, when you're looking at 1, 2, and 3 here, does this basically just generate, just doesn't give you anything. So you keep generating until you get something, right? Because you could actually, when you generate, you might not actually get anything. Okay, fair enough. Make 19 calls. Most of the time, you're going to get at least one integer. Okay, fine. So if you're less than this basically 0, kind of 0 off here, divided by 0 off here. If you're less than this value, then you're going to take the digit and add 1. So you get one number from 1 through 10, and that's a random. Yeah, I guess you just get a string of random digits here. That's pretty much. Okay, I think I understand. So basically, you're just generating a string of random digits. And what the probability of each digit being any particular value is pretty close to equal for each digit, and then you're gonna extract each digit. And so if you're less than this number, then every digit will give you a number, an integer. So in a huge number of the cases, 87.73 cases, you're gonna get 16 integers. And then there's sort of like from that point upwards. Basically, if you're over these digits, you get fewer and fewer integers. Okay, pretty interesting. He's saying that's pretty close to the theoretical limit. All right. Because you get roughly 16 integers, 85%, over 87% of the time per 19 calls. That would be right if you did 16. If that was the only thing you considered, you have 16 over 19, and that's 85% of the time. Or rather, 19 calls would give you 19 calls would give you 16 numbers, and that's 80% of the time. 0.8773. You'd actually divide by 0.8773, so it's 19 over 16 divided by 0.8773. No, divided by, hold on, did this wrong. 19 over 16 divided by 0.8773, and I couldn't really give you the rationale exactly, but that should give you, yeah, and then it's actually better than that, because you're not adding the other pieces, but that gives you less than 2 calls each, right? The reason why you divide by this number is, well, actually you'd say 87.7, you'd say 0.8773% of the time you're going to be doing, it's going to take you, it's going to say 19 calls will give you 16 integers. Give you 16. So that's how much that portion contributes, I guess, to the expected value. And then you have another portion, which is the next set of cases, right? Which is like 80. It would be like for the next value of 1. I think I'd probably just use Monte Carlo to do this, but you can calculate this. It would be like the difference between this number, the number of cases, I guess, between this, so this is sort of like the cumulative value. There's sort of like a, I guess not the cumulative amount, but there's like some percentage of cases between this number and just 11 and all zeros here, and those would give you 15 integers, and then there's a smaller number that would give you 14, a smaller number that gives 13, and so on, and that would actually drive this number up. I was wrong actually about dividing this. You do have to actually multiply, and it's 19 over 16. No, 19 over 16. I think it's the other way around. I think it's how many calls per integer do you need? Yeah, 19 over 16, and that's going to be 0.8773% of the time, and then you're going to add now. Yeah, I think you add. Yeah, you just add. It's actually, it's the other way around. I'm sorry. It's the other way around. It's okay. It's this way. Yeah. No, that's fine. That's fine. You would add these. You do 15. You do 16 times this number 0.8773 times the probability, and then you would divide by 19. Sorry, it's divide by 19, right? What do we want to? We want to know what the average number of calls per integer. The number of calls per integer. I think Monte Carlo is the simplest way to do it, but I want to say that is you can break this up into cases and figure out this percentage of the time it's going to take this many call, right? This you're gonna call 19 and get 16. A certain number of time you're gonna call 19 and get 15, right? All of those numbers give you how many calls in that percentage, I think you take the sum of those things. I think you just take the sum. That gives you the total expected number. Yeah. Yeah, because the other numbers will be very small. That's the thing. Because I was like, well, what if the other numbers are like, you know, kind of big? Like, wouldn't that push you way over 1.2 or roughly 1.2? And no, actually, the numbers are pretty small. Because these percentages are really small. 0.8773 is pretty big, but once you start dropping in digits here, then these numbers get smaller and smaller. The weight for those cases is higher in the sense that you're going to generate less integers. So 19 divided by 15 is larger than 19 over 16, and so on. That's going to get bigger and bigger, but it's sort of logarithmic each factor, because you're moving down a digit at a time here. Yeah, that's kind of interesting. But yeah, you end up with 1.199 if you calculate it. And there's actually a point where you get no integers, a certain amount where you get no integers, and I want to say that's, yeah, that actually gives you like a division by 0 the calculation that I was about to give you, which means that actually you have to counterbalance that, you need to say, not to counterbalance, to take that into consideration, you actually need to show that there is a certain number of times there's expected number of times we have to call. Yeah, actually, you could do, you would have to call this whole thing a certain number of times until we get at least one integer. And you can calculate how many times that would take, how many calls that would take, which would be actually these numbers inverted, right? That's the number of times you have to call this function to get at least a number, and then of those cases, what the probability is. How many calls? What's the probability? Yeah, what's the average number of calls per integer given that we're in this range, right? Given that we know we're going to get at least one integer, and then you could take that probability and then multiply it by how much probability it takes to actually get, to be certain that you'll get an integer. I think that works. I think you do it that way. Yeah. But yeah, but Monte Carlo works too. I think that's what he used. Just run it a bunch of times and you get an idea. So that's pretty cool. It's 1.2 is very close to the theoretical limit, right? Theoretically, it's 1.8. I don't know where he got this log 10 over log 7 for the efficiency. Oh, I think I understand. Yeah, because you have a range of size 10, and you're trying to get it. You're trying to roll a range of size 10 with a range of size 7, and so you start trying to increase the size of this range. Well, actually, I don't know. How did he get this? How did he get this limit? Where did I don't know how he did that. 49 random states, waste 9 of them. I don't know where this comes from. The greatest efficiency that we can have is log 10 over log 7. Is that right? In the inverse of this, or it's the efficiency would be, well, how many states do we make use of? 20%, which is, I don't know where he got this from. I take it back. I don't know. I don't have a clue. Pretty interesting that this is the theoretical limit. How do you prove that? How do you know that? And finally, need to decide the power in advance. Have a concern. How can we find a magic power like 19 or 7? Don't need to. Can you improve solution 1? You cache a big random number, and when we need a Rand10, we take a part from it. This solution is 1.183. Ah, that's interesting. So cache upper self, cache self upper 0, 1. While upper is less than 10 raised to the 9th, so a billion. Cache upper, cache times 7 plus self Rand7 minus 1 upper times 7. So cache modulo 10 plus 1, self cache self upper equals cache over 10 upper divided by 10, self dot count 10 plus equals 1, test. Oh, so this is probably just to do the this is probably just to do the this is probably to just to do the what do they call that? This is probably just to do the Monte Carlo calculation to see how well this does. Okay, I see. So basically, you have a running total of a gigantic power, some gigantic power of 7, and you just take a what do they call that? A you take some running total of some gigantic power of 7, and you just keep peeling off the into the ones place digits as a digit from 1 to 10 and add 1 to it each time, and then your number is it's some power, it's some what do you call that, like it's some number generated by multiplying by 7, but basically it's a number it's a base 7 number. That's basically what it is. It's a randomly generated base 7 number, right? And what you're randomly generating is each base 7 digit of that base 7 number. And then what you're doing is you're converting that to a base 10 number by just taking the least significant portion of it. And yeah, and you just keep increasing you kind of take a piece off of it, and you just keep increasing that number add another base 7 number to the left side until as you need more, you keep doing that. And actually, yeah, you can just keep this number, keep it very large, I guess. Excuse me. I'm not sure what this upper is, actually. This is a little bit confusing. There's a cache and there's an upper. Upper is less than this. You don't actually need this upper portion. I don't think so. I think you can just literally, you can do something like this. So this is pretty interesting. I'm glad we looked at this. Glad that we looked at this this discussion. Took some time to do that. Give me one moment here. I just want to save this solution. Call this, what is this? 470. implement Rand10 using Rand7. Okay, and this is going to be 1, first one. Alright, so we have that saved. Now that's saved, what I want to try to do is right, so we're going to take a huge integer and we're going to have I'm going to say just current, right? And we're going to say set that to 0, and we're going to start by, we're going to say while current is less than 10 to the 9th, 1, 2, 3, 4, 5, 6, 7, 8, 9. While current is less than 10 to the 9th, we're going to say current times equals, current is going to be 7 times it itself plus Rand7 minus 1. Right? So we do, current equals 7 times current plus Rand7 minus 1. Keep doing that until this number is at least a billion, right? And then we're going to say, actually we're going to have private members here. Private current right? And we're going to say ret is going to be current modulo 10 plus 1, and we're going to say current divide equals 10, and return ret. All right, something like this. I think this works. I don't know what's going to happen if we do this. Oh, okay. 1, 10, 100, 1,000, 10, 1,000, 100, 1, 2, 3, we'll do 500 and 1,000, and just some random numbers here too. Yeah. All right, let's go for that. See how we do. See if this works. See if this works. I don't know what's going to happen here. Hey, okay. Sweet. All right, let's go for it. Okay. It's about as efficient as the other one. Wait, really? It feels like that's almost disappointing. Really? Wouldn't this be? It doesn't have to be a billion. Let's make it like 1, 2, 3, 4, 5. Right? 10,000. This really doesn't need to be that big. So you pay this upfront cost. Pay this upfront cost to create a relatively large number, and then what does this look like now? Oh, okay. Faster than 92%. It's a little bit faster. What if we did an integer? Right? Because now it's only 10,000. Is that any faster? Maybe? I don't know. Okay. We're a little bit faster doing that. We could probably do better than that. We could probably do like 1,000. A few extra upfront calls to Rand7. And now over on the average, it becomes pretty efficient. I don't know if we do 100. That seems questionable. Okay. It's pretty quick. It's pretty quick. I don't know if we could do 10. 10 is I don't know if we could do 10. 10 won't work properly. 10 I think is the wrong answer. Yeah, 10 doesn't work. You have to do at least 2 digits. At least 2 digits. While efficient, relatively efficient, should give us pretty good bound for the number of calls per. Should give us a pretty good bound for the number of calls required. Excuse me. Yeah, this should give us a pretty good bound for the number of calls required to generate these numbers. Really interesting. I don't know what exactly is happening here, but yeah, I think the probability of each number is roughly the same. Of each digit ending up in the ones position is roughly the same. It's kind of hard to tell. It's kind of hard to tell what it is. It's kind of like a random number. Yeah, I don't know. I don't even know how to think about this exactly, but this seems correct too. I like this. I like this solution. I think this is pretty good one. It's relatively quick. I could not tell you though how to get the limit and how to get the optimal, and then also how to calculate the optimal, and then how to actually implement something that's optimal. That I don't really know. I don't really know why. Log 10 over log 7 somehow. I don't know, man. I think the reason it's log 10 over log 7 is because it's log base 7 of 10. I think that's what it is, right? If you take log base 7 of 10 digits, right, into log base 7, that's the same thing as log 10 over log 7. Yeah. I think I understand. I think I get it. And the reason why you take that logarithm is, come back to that in a second. The reason why you take that logarithm is because log 10 base 7, why is that the optimal number of calls required? Well, because you're generating numbers that are base 7. And then you're going to, for each call to generate the number that's base 7, you're going to you know what, I think I did this wrong. I think I did this wrong. I think this is not as fast as it could be because of the cache. You do want to have a cache that you pull numbers from. Yeah, because this guarantees that you always have an extra call averaged across your entire. So for like small values of n, this is inefficient. So you do want to have some kind of a cache going on here. What did he do? He had some upper thing going on. So we'll come back to that in a second. But I think the reason is because you're generating a number, a random number, it's base 7, and then that's why. Because you're generating a random number that's base 7, and you're getting a number of digits. You're getting a log 10 number of digits for a base 7 number. That's why. So in the perfect case, the number of calls you make will generate some base 7 number, and then you're taking a log base 10 of that number, and that's giving you the number of. So it's x calls. X calls gives you some number base 7, call it k, base 7, and then you're taking the logarithm base 10 of k, which is going to give you log base 10 of k is going to give you x prime, we'll call it, which is the actual number of numbers. And so we want the actual number of numbers. You want the number of calls per x prime, which is k over log base 10 of k. Where k is some number base 7. And that would be that's the theoretical limit for our approach here. And k could be really any number, I guess. Well, k is like a very large number, presumably. I think something like this. If k is 7 over, if you did log base 10 of 1, let's do like, I don't know, 10 raised to the 9th divided by log of 10 raised to the 9th. No. I don't know if this makes any sense. I don't know if this makes any sense. It's not k though. It's x. It's x over. It's x over. Which the number of calls it took to get to k is log base 7, because k is base 7. So x is log k. Right, so x is log k, log base 7 of k, and x prime is log base 10 of k. And so now you're looking at log base 7 over log base 10, which is let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. Do log of that divided by log of 7 divided by log of 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by this number. There you go. Yeah, so this ends up being, if we use change of base formula, this ends up being log base 7, log base 10 of k over log base 7 divided by log base 10 of k, which then gives us wait, what? 100 log base 100 divided by log base 7 should give you, that's log base 7 of 100, right? So if you take 7 raised to this power, that should give you 100, yeah, okay. So log base 10 of k, log base 7 of k can be rewritten as log base 10 of k over log base 10 of 7, right? Divided by log base 10 of k, which gives you 1 over log base 10 of 7, which is exactly 1 over which is actually negative log base 10 of 7, no, I don't know. What is this? Somehow this is log 7 inverted is 1.83. Is the number, is basically the number we're looking for. I'm just going to charge the headset here. What am I doing here? Somehow this is also equal to log of 10 over log of 7, which that I don't quite understand. Well, yeah. Log 10 of 7 is equal to log of 10 over log of 7. Yeah. And 1 over that, or no, excuse me, it's log of 7 over log of 10. Wait, what? Log of k base 10 over log of 7 base 10. Yeah, it's a change of base. Yeah. So this is log of 7 base 10 over log of 10 base 10. Which is true, right? This is just 1, and this is log of 10, 7. And so 1 over that, 1 over log, oh, wait, of course, this is log 10 over log 7. Duh, 1 is just log 10. I don't know why why I struggle with that so much, but yeah, it's log 7. This is 1 over log 7. Ultimately, 1 over log 7. Yeah. And you can change that base however you want, but right, 1 over log 7. Okay, cool. Neat. I think I get it. That's optimal for this particular algorithm, which is pretty good. It's not bad at all. Okay, I get it now. My solution is not quite as good because I need to, oh, this is someone else's 3-line solution. What do they get? 36 out of 26. 36 over 26 is 1.38. This is 49 out of 45. This is pretty good. Whoa. Time complexity. Oh, complexity. That's what it was. Yeah. So 45. If you're greater than 45. No, but this requires 2 calls. No. This is not. Rand7, Rand49, Rand45, Rand9. Oh, never mind. Okay, gotcha. 49 out of 40. No, but this requires I mean, of course it's constant because you only need 2 calls, right? I mean, no, that's not. All right, interesting question, but this is an interesting solution, but this isn't the best. It's not a particularly good solution. Not particularly clever or innovative. I mean, it's not bad. Don't get me wrong, it's not bad, but it's not quite like this one. This one is really, this is taking something that's, you know, a new idea and making things more efficient. But I think you need to use the cache, otherwise you're stuck generating extra calls, and for smaller numbers it's pretty bad, for smaller values of n. But I think you're kind of stuck always getting an extra value of n anyway, extra call, because this cache, this upper times 7, while it's less than a billion, which is a bunch of calls of 7, basically just a bunch of calls. So you fill up the cache initially here, and then now you drop the upper in the cache. Actually, every time you call, you're guaranteed at least 1 call, because this upper has to go back up past this bound. So actually, mine is actually probably more efficient than this, believe it or not. I think the one I wrote is better then, because you're always guaranteed this extra call no matter what. Because this cache has a whole bunch of extra calls. By the time you're done, you don't actually finish the cache, because this upper guarantees that the cache is always filled, and kind of filled to the brim, pretty much. Pretty much the cache is always filled to the brim, which it doesn't need to be. But you can just bound the cache itself to keep it filled. You don't need this upper. So actually, both of our solutions are about the same speed. The one that I wrote. This is the equivalent form of that. Okay. So sweet. All right. Done. Nice. Saved it because I thought that was good. Alrighty. Thank you for watching. I'll talk to you soon. Have a good rest of your day. That was fun. That was interesting. I've struggled with this question. I've struggled with this question for quite some time. So I'm grateful to have seen it. Grateful to have seen it. Yep. Thank you for watching. Talk to you soon. Have a good rest of your day. Take care. I don't know what I'm doing after this.